Somewhere over the middle of the Pacific Ocean, right now, there is a river in the sky. You can't see it if you look up. There's no water glinting in the sun, no current you could point to. But it's there, about a mile above the waves, moving faster than most hurricanes, carrying more water than the Mississippi River carries at its mouth. Multiply the Mississippi's flow by 25. That's roughly what's moving through the air above the Pacific right now, heading straight for California. I know that sounds like an exaggeration. It's not. And I know the title of this video sounds like clickbait. A powerful atmospheric river is taking aim at California. But that's not quite the full picture, and here's what I mean by that. This isn't one storm. It's a delivery system. It's the sky organizing itself into a hose and pointing that hose at a coastline where 20 million people live, where hillsides are already scarred from wildfires, and where the ground is not ready to drink what's coming. By the end of this video, you're going to understand three things. First, what an atmospheric river actually is, and why meteorologists describe it with the same language they'd use for a river on the ground. Banks, flow, discharge, the whole vocabulary. Second, you're going to understand how scientists figured out these things even existed, because for most of history, nobody knew they were there, and the way we found out is genuinely one of the best detective stories in modern weather science. And third, you're going to understand what this specific kind of event means for the place you live, whether that's a hillside in Malibu, a farm in the Central Valley, or a city street 200 miles from the nearest ocean. I want to be upfront with you about something before we go further. I'm going to walk you through the scary part first. The flooding, the debris flows, the specific mechanics of how this kind of storm kills people. And only after that am I going to walk you through the reassuring part. The part where I tell you what actually protects you and why most people who prepare properly come through these events just fine. I'm doing the scary part first on purpose. If I gave you the comfort first, you'd stop listening before you got the information that actually keeps you safe. So stay with me through the hard part. It's worth it. Before I get into the science, I want to ask you something, because I actually want the answer. Down in the comments, tell me how far you live from the nearest coastline or the nearest hillside that's burned in the last few years. I read these, and I want to know how many people watching this are actually standing in the path of what I'm about to describe, versus watching from somewhere this could never reach. If you're new here, this channel breaks down one real, research-backed natural hazard every single week. Not the scary headline version, but the actual mechanism underneath. It, explained the way I'd explain it to a friend at my kitchen table. That's a standing promise, not a one-time video, so if that's useful to you, subscribing means you won't miss the next one. And if you're finding this helpful so far, hitting like right now genuinely does one specific thing. It helps this video reach other people who live near a coastline, or a burn scar, and have no idea a storm like this is even a category of weather, let alone one that might be headed their way this week. That's not me asking for a favor. That's just how the next person finds this before their own storm arrives, instead of after. Let's start with what this thing actually is, because atmospheric river is one of those terms that sounds like a metaphor invented by a headline writer. It isn't. It's a precise scientific term, and once you understand the mechanism, you'll never look at a rainy week in California the same way again. Picture the ocean near Hawaii. The water there is warm, and warm water evaporates constantly, filling the air above it with moisture. With actual water vapor, invisible, floating molecules of water suspended in the atmosphere like steam over a pot that never stops boiling. Normally, that moisture just spreads out lazily in all directions. But sometimes, a very specific kind of wind pattern sets up. A low-pressure system spins near the Gulf of Alaska, and it acts like a fan positioned just right, pulling all that moist tropical air into a long, narrow ribbon instead of letting it spread out. That ribbon can stretch for 1,000 miles, sometimes 2,500 miles, but it's usually only a few hundred miles wide. Think about that shape for a second. It's not a blob covering an ocean, it's a hose. A long, narrow, aimed hose of airborne water, and the nozzle end of that hose is often pointed directly at the coast of California. That's the central image I want you to keep in your head for the rest of this video. A fire hose in the sky, and the mountains of California are standing in its path. Let's slow down on that low-pressure system for a second, because it's doing more work in this story than people realize. Picture a low-pressure system like a slow spinning drain sitting out near the Gulf of Alaska. Air spirals into it the same way water spirals into a drain, and that spiraling motion is what grabs the moist tropical air near Hawaii and redirects it instead of letting it just drift north on its own in a wide, lazy sheet. Without that spinning low-pressure system acting like a steering wheel, all that moisture would probably just spread out over thousands of miles of open ocean and never organize into anything dangerous. It's the combination of the warm moisture source and the exact position of that spinning system that turns background humidity into a targeted hose. Move that low-pressure system a few hundred miles north or south, and the same amount of moisture might get steered toward Washington, state instead of California, or might miss the coast entirely and spin harmlessly out over open water. That's part of why forecasting exactly where an atmospheric river will make landfall, even a day or two out, is still genuinely difficult. Small shifts in the steering pattern can move the aim of the hose by 100 miles or more, and 100 miles matters enormously when the difference is a farm town getting normal winter rain and a canyon community getting a flash flood. Here's the number that makes this real, translated into something you can actually picture. The strongest atmospheric rivers carry an amount of water vapor that, if you could somehow freeze it all and stack it up, would be the equivalent of Earth's biggest rivers combined. The Amazon, the Mississippi, the Congo, moving sideways through the sky instead of down through a channel. Scientists measure this in a unit that sounds intimidating but isn't: kilograms of water passing through each meter of the river's width every second. A strong atmospheric river typically moves at least 250 of those units. The very strongest ones move more than 750, translated into plain English. A strong one is dumping enough water in the air, moving through the sky to fill roughly 1.5 Olympic swimming pools every second, just from that single slice of atmosphere. And that hose can stay pointed at the same stretch of coastline for 18 hours, 24 hours, sometimes longer. Now here's where the mountains come in, because this is the part that turns a lot of rain into a genuine disaster. When that moist air runs into California's mountain ranges, the Coast Ranges first, then the Sierra Nevada, it has nowhere to go but up. Air that rises cools. Air that cools can't hold as much water vapor, the same way a cold glass can't hold as much sugar dissolved in it as a hot. Glass can, so the water has to come out. It falls as rain, and if it's high enough and cold enough as snow, this effect has a name, orographic lift. And I'll only explain it this one time. It just means mountains force air upward and upward air dumps its water. That's it. That's the whole concept. This is why the same atmospheric river can drop 2 inches of rain on Sacramento and 20 inches of rain in the same storm on a mountain slope 40 miles away. The hose doesn't turn off. It just gets squeezed by the terrain, the same way pinching a garden hose makes the water shoot out harder in one spot. There's a second layer to this that most people never think about, and it's the difference between rain and snow, and why that difference matters more than you'd expect. When an atmospheric river is cold enough, high up in the mountains, all that moisture falls as snow instead of rain, and it stacks up in the Sierra Nevada as snowpack, essentially a giant, slow-release reservoir sitting on the mountains, holding water until spring, when it melts. Gradually, and refills rivers and reservoirs over months instead of days. That's the good version of this story. But when an atmospheric river arrives warmer than usual, and warmer atmospheric rivers have become more common in recent decades, the rain-snow line, the elevation above which precipitation falls as snow instead of rain, climbs higher up the mountain. That means rain falls on ground that would normally be catching snow, and worse, warm rain falling directly onto an existing snowpack can melt that snow rapidly from the surface down, adding the melted snow's volume on top of the falling rain's volume. Hydrologists have a specific, somewhat alarming term for this combination: rain-on-snow event. It's one of the most efficient flood-producing mechanisms in the entire California water system, because you're not just getting the rain, you're getting the rain, plus weeks or months of stored-up snow, all trying to funnel down the same rivers at the same time. This is one of the places where the honest uncertainty I mentioned earlier really matters, because it's also one of the clearest fingerprints of a warming climate on this whole system. As average temperatures rise, even slightly, the elevation where snow turns to rain climbs with it, which means a larger share of the Sierra Nevada's total precipitation is expected to fall as rain instead of snow in future decades, compared to a century ago. Researchers don't fully agree on exactly how much this will change the frequency of rain-on-snow flood events specifically, because it depends on so many overlapping factors. How warm individual storms are, how much snowpack has already built up before they arrive, how quickly reservoir operators can adjust. But there is broad agreement on the underlying trend: a shrinking snowpack that melts earlier and less predictably than the snowpack California's entire water system, from farms to cities, was originally engineered around. That's not a dramatic, single-storm kind of danger. It's a slower, structural one, the kind that doesn't show up as a viral headline, but quietly reshapes how much margin for error the state has left the next time an atmospheric river family rolls through. I promised you a detective story, and this is one of the good ones, because for most of the 20th century, meteorologists knew California got hit by big, wet storms out of the blue, Pacific. But they didn't know why some winters brought catastrophic floods while others, with seemingly similar weather patterns, didn't. Old-timers on the West Coast had a folk name for it long before scientists had a real explanation. They called it the Pineapple Express, because the moisture seemed to come from around Hawaii, and it felt almost tropical compared to a normal winter storm. But a nickname isn't a mechanism nobody could explain with real physics. why the moisture behaved the way it did. The breakthrough came from an unexpected direction, not from meteorologists staring at California, but from atmospheric scientists studying the global movement of water vapor as a whole, trying to figure out how moisture gets transported around the entire planet. In the 1990s, researchers building detailed computer models of global water vapor noticed something strange in the data. The vapor wasn't spread evenly through the atmosphere the way older, simpler models assumed. It was concentrated into narrow filaments, thin, fast-moving streams, most of the planet's total north-south water vapor transport happening inside a handful of these ribbons at any given moment, even though those ribbons covered only a small fraction of the sky. That was the reveal. The moisture wasn't diffuse, it was channeled. It moved like water in a riverbed, not like fog spreading through a room. That's the moment the term atmospheric river was actually coined. And it wasn't a poetic flourish. It was the most literally accurate description available, because these things really do behave like rivers, with a defined channel, a measurable flow rate, and a destination. Once scientists had that framework, old satellite images and old flood records suddenly made sense in a new way. Storms that had been treated as mysterious one-off disasters turned out to be part of a recognizable, trackable category of weather event. The 1861 and 1862 California flood, the one where it reportedly rained almost continuously for over 40 days, turned the entire Central Valley into an inland sea roughly 300 miles long and forced the state government to temporarily relocate because Sacramento was underwater. That event has since been reconstructed by researchers using tree rings and old sediment layers, and it lines up with what we now understand as a relentless parade of atmospheric rivers, one after another, for weeks. The mystery wasn't solved by watching one storm. It was solved by realizing there was a whole invisible category of storm that had been hiding in plain sight the entire time. It's worth spending a moment on that 1861-62 flood specifically, because the details of it read less like history and more like a warning letter written to the future. Contemporary accounts describe rain falling, with only brief pauses for over a month straight across much of the state. The Central Valley, normally dry farmland stretching for hundreds of miles, became a temporary lake so large that boats reportedly navigated between towns that are nowhere near water today. Livestock losses were catastrophic enough that some historians consider the flood a major turning point in the collapse of California's cattle ranching economy, which had dominated the state before that winter. The state capital itself flooded so badly that the governor was reportedly rowed to his own inauguration, and state government operations were relocated for a period because Sacramento was underwater. What makes this relevant today isn't just that it happened once. It's that researchers studying sediment layers and tree ring records have found evidence of similarly extreme, sustained atmospheric river sequences occurring roughly every 1 to 2 centuries throughout the past several thousand years, which means the 1861-62 flood wasn't a freak accident outside the normal range of California weather. It was an example, on the more extreme end, of something the state's climate is fully capable of producing again, at any time, on infrastructure and population scales that make the original event look almost gentle by comparison. What makes this detective story even better is what happened after the initial discovery, because naming something and actually being able to track it in real time are two very different problems. For years after the term atmospheric river entered the scientific vocabulary, researchers still couldn't watch one form and evolve the way you'd watch a hurricane spinning on satellite footage, because water vapor itself is invisible to a normal camera. The breakthrough that let scientists actually see these rivers came from satellites carrying microwave sensors, instruments that can measure the amount of water vapor in a column of atmosphere by detecting how that vapor absorbs and emits microwave radiation, the same general kind of technology used in a microwave oven, just pointed outward at the sky instead of inward at food. Once those sensors were flying regularly, scientists could finally produce something like a live weather map, but for invisible airborne rivers instead of visible clouds. That's the tool that turned atmospheric rivers from a theoretical pattern buried in decades of old data into something forecasters could watch, approach the coast, days in advance, the same way you'd watch a hurricane's projected path on the news. It's a good reminder that most scientific breakthroughs aren't a single lightning bolt moment. They're a discovery, followed by years of engineering work to build the tools needed to actually use that discovery. I do want to pause here for the myth debunking section, because anytime a video talks about extreme weather-threatening California, the comment section fills up with a few very predictable claims. And I think you deserve better than either blind panic or blind dismissal. First, no, this is not geoengineering or intentional weather modification by a government agency. Atmospheric rivers have been documented in tree ring and sediment records going back over 1,000 years, long before anyone had the technology to manipulate weather at this scale. And the physics, warm. Ocean, low-pressure steering pattern, mountains forcing air upward. is straightforward, observable, and reproducible. Second, no, scientists are not exaggerating the danger to get funding or to make headlines. If anything, atmospheric river researchers have spent the last 2 decades trying to get more public attention on these events, because for a long time, they were underappreciated compared to hurricanes and tornadoes, even though averaged over a whole season, they deliver a huge share of the West Coast's total water supply and a huge share of its flood damage. Third, and this one matters, no single video, including this one, can tell you exactly how bad a specific future storm will be, down to the inch. Even the scientists who study this professionally will tell you they don't fully agree on exactly how a warming climate is going to change the frequency of the very strongest atmospheric rivers. Some models suggest we'll see more of the extreme ones. Some suggest the total number might stay similar while individual storms carry more water. That uncertainty is honest, and I'd rather tell you that than pretend this field has everything figured out. There's one more. Myth worth addressing directly, because it comes up constantly in the comments on videos like this one. The idea that a single megastorm could somehow solve California's drought problems for good, so intense rain should be treated as purely good news. It's true that a strong atmospheric river season can dramatically improve reservoir levels and snowpack in a single winter, but water managers will tell you it's not that simple, because California's reservoirs are deliberately kept partly empty heading into the wet season on purpose, to leave room to catch floodwater and control the rate at which it's released downstream. A reservoir that's completely full, when a huge atmospheric river arrives, has nowhere to put the incoming water, except to release more of it downstream immediately, which can turn a beneficial storm into a flood control emergency. So more rain isn't automatically more water security. It has to arrive in a way the existing infrastructure can actually capture and hold, which is part of why California's relationship with these storms is genuinely complicated rather than simply good or bad. Now let's get back into the mechanism, because there's a second half of this story that most videos skip, and it's arguably more dangerous than the rain itself. California's wildfires leave behind more than blackened hillsides. They leave behind soil that has been chemically altered by intense heat. When certain plants and organic material burn at high temperatures, they release waxy compounds that seep into the top layer of soil and then, as the ground cools, harden into something close to a wax coating just beneath the surface. Scientists call this a hydrophobic layer. Hydrophobic just means water repelling. Picture wax on a car hood, the way rain beads up and rolls off instead of soaking in. That's what a burned hillside looks like to falling rain. The water doesn't sink in and get absorbed by roots and soil the way it would on a healthy, vegetated slope. It hits that waxy layer and runs straight across the top instead, picking up speed, picking up loose ash, loose soil, and loose rock as it goes. Here's where the two threats, the atmospheric river and the recent wildfire, combine into something far worse than either one alone. On a normal hillside, even heavy rain mostly soaks in. On a recently burned hillside hit by an atmospheric river's intense rainfall rates, the water doesn't soak in. It sheets across the surface, gathers volume and speed, and picks up so much loose material that the mixture stops behaving like water at all. It starts behaving like wet concrete moving downhill at highway speed. This is called a debris flow, and it is, statistically, one of the deadliest hazards connected to atmospheric river events in California. These flows can move faster than a person can run. They can carry boulders the size of cars, and they typically give almost no warning. Sometimes just seconds between the sound of rumbling and the flow itself arriving. The most devastating recent example happened in Montecito, where an atmospheric river dropped extremely intense rainfall onto hillsides burned bare. Just weeks earlier by a major wildfire, and the resulting debris flow moved through neighborhoods in the middle of the night, killing more than 20 people, many of whom had no warning at all before it reached their homes. To understand why debris flows are so much more dangerous than ordinary flooding, it helps to compare the two side by side. Ordinary floodwater, even fast-moving. Floodwater is still mostly water. It's dangerous, it can sweep a person off their feet, but it behaves roughly the way you'd expect water to behave. A debris flow is a completely different physical substance. Once a slurry of ash, soil, and rock reaches a certain concentration, sometimes 60 or 70% solid material by volume, it stops behaving like a liquid with some stuff mixed in and starts behaving like a semi-solid mass that moves as a unit, the way wet concrete moves when it's poured, except this version is moving downhill under gravity at speeds that have been measured at over 20 miles per hour on steep terrain. That combination, near solid density, moving at highway speed, arriving with almost no warning, at night during a power outage when most people are asleep, is exactly why debris flows produce a disproportionate number of fatalities compared to their overall frequency. It's genuinely one of the most underappreciated natural hazards in the entire country. precisely because it doesn't have the cultural profile of a hurricane or a tornado, even though, storm for storm, it can be just as lethal in the specific zones where it occurs. I want to give you the reassuring part now, the release valve, because it's important that you don't walk away from that last paragraph thinking there's nothing you can do. Here's what that danger does not mean. It does not mean every hillside near you is one storm away from collapsing. Debris flow risk is highly specific. It depends on recent burn history, usually within the last 1 to 5 years, slope steepness, and rainfall intensity, not just total rainfall. Most of California is not sitting on freshly burned steep terrain right now. Emergency management agencies specifically map recently burned areas after every major fire and issue targeted evacuation warnings for those exact zones when an atmospheric river approaches, precisely because this risk is now well understood and specifically tracked, unlike in earlier decades when the connection between fire and flood risk wasn't as widely appreciated by the public. But I want to escalate again, because there's a second-order effect that most coverage of these storms completely ignores, and it's one you've probably never thought about: infrastructure fatigue. A single atmospheric river is a weather event, a sequence of them arriving, back-to-back over a 2 or 3 week period. What meteorologists sometimes call atmospheric river families is closer to a slow-motion structural test on the entire state. Reservoirs that were managed to have room for one big storm can fill up faster than expected when storm after storm arrives with little gap between them. Levees along the Sacramento and San Joaquin rivers, many of them built more than a century ago, are engineered with a certain amount of expected saturation in mind. Earthen levees that stay wet for weeks at a time are more prone to seepage and, in worse cases, breach than levees that get wet, dry out, and reset between storms. Storm drains in cities can handle one intense storm's worth of debris and leaf litter. They're far more likely to clog and cause street flooding on the 3rd or 4th storm in a row when nobody's had time to clear them. This is why emergency officials sometimes seem more worried about the 4th storm in a series than the first one, even if the 4th storm on paper is weaker. The ground and the infrastructure remember the storms that came before. Levees deserve a bit more explanation because most people have never really thought about how one works. A levee is essentially a long wall of packed earth running alongside a river, built to hold back water that would otherwise spread out across the surrounding land during a flood. Picture the wall of a sandcastle holding back the tide. It works fine for a while, but if the water stays high against it for hours and hours, the water starts to seep into the wall itself, not over the top, but through the material the wall is made of. That's what happens to earthen levees during a prolonged atmospheric river event. Sustained high water, hour after hour, can cause seepage to develop deep inside the levee, sometimes creating hidden weak points called boils, where water begins pushing up through or around the base of the levee on the dry side. A warning sign that engineers watch for constantly during major storms. Most of the time, levees hold. But a levee that just endured 2 weeks of sustained high water from an earlier storm in the sequence is starting the next storm already weakened, already saturated, already closer to its failure point than it was at the start of the season. That's the entire logic behind why a storm family, several atmospheric rivers back to back, poses a risk that's genuinely larger than the sum of its individual parts. Let's talk about the real numbers now, translated, because I don't want to just throw statistics at you without telling you what they mean in a life you'd actually recognize. A single strong atmospheric river event can deliver 30 to 50% of California's entire annual precipitation in a period of just several days. Translated, imagine your whole year's supply of something, paychecks, groceries, whatever fits your life, arriving in one enormous delivery instead of spread out evenly, and having to figure out where to store all of it all at once without it overflowing. That's what California's water infrastructure has to manage during one of these events. Rainfall rates on the windward side of coastal mountains during an intense atmospheric river can exceed 1 inch per hour, sustained for many hours in a row. Translated, that's roughly the equivalent of a very heavy, drenching thunderstorm, the kind that makes driving nearly impossible. Except instead of lasting 20 minutes and moving on, it can sit over the same slope for 6, 8, 12 hours straight. The strongest atmospheric rivers on record have been estimated to carry a water vapor flux more than double the flow rate of the Amazon River, the largest river on Earth by volume. Translated, the sky, over a stretch of ocean a few hundred miles wide, is moving more water than the largest river system on the planet, except it's doing it invisibly, a mile above your head, until it hits a mountain and remembers it's supposed to be liquid. And here's a number about benefit, because these storms aren't purely villains in this story, and I think that nuance actually makes the danger easier to respect rather than dismiss. In an average year, atmospheric rivers supply somewhere between 30 and 50% of the entire West Coast's annual water supply. the snowpack that fills reservoirs, the water that irrigates a huge share of the country's fruits and vegetables, all of it substantially dependent on these same storms arriving on a roughly normal schedule. Translated, the thing that can flood your street in January is very often the same thing that keeps your tap running in August. California's relationship with atmospheric rivers isn't simple. The state needs them and fears them in the same breath, sometimes in the same week.